Hi to everyone. This is Soutis from University of Manchester, Professor of Aerospace Engineering. Before I start my talk on toughening up composites, I'd like to take the opportunity to thank the President of the Society, Professor Francesco Iacovello, and the organizing committee for giving me this opportunity to present at the first virtual European conference on fracture. Manchester is Britain's first university of the industrial age, with very strong research on advanced materials, from lightweight alloys for planes, trains, ships and cars, to high temperature materials for jet engines and power generation, to electronic ceramics and polymers, to biomedical materials for implants and tissue engineering, to engineer smart textiles and composites. And composites is the topic of this presentation. More specifically, I'll talk about carbon fiber composites, continuous fibers, or woven fabrics impregnated with epoxy resins to fabricate multi-layered composite structures. What are the benefits? Why are we using these materials? We save weight, they provide high strength and stiffness, we can tailor mechanical properties, we can achieve complex shapes and contours. They reduce part count over metallic equivalent, they require less machining, they do not corrode in aggressive environments, they provide very good fatigue resistance with the potential for embedded functionality that can be related to damage sensing and self-healing. Where are they used? Very extensively these days. You can find them in aerospace and defense applications, energy, wind energy, marine construction, and transportation. Carbon fiber composites have been around for almost 60 years now, with the first commercial product appearing in 1983 when Dunlop produced their first carbon fiber tennis racket, and in 1995 McLaren used carbon fibers for their Formula One car. Composites enable innovation. We've said at the beginning that they enable us to fabricate and achieve complex shapes. Here you can see the winglet of the Airbus A350, where the entire section is made out of carbon fiber, while the aircraft contains more than 52% of carbon fiber composites. Here is the complex inlet duct of the F-35, manufactured by Advanced Tape Placement, a very complex shape that we wouldn't be able to produce from metallic materials. It would be too heavy and the aircraft would lose its stealthiness. We also mentioned that composites offer us excellent fatigue behavior. And here we can see a comparison between the more metallic Airbus A380 window compared to the bigger cutout that you can be found in the Boeing 787. Of course, we know that everything fatigues, and carbon fiber composites also get damaged when they're loaded at the static loading or dynamic loading. And here we can see a simplified 090 laminate under tensile loading, where at some critical stress or some critical applied load, damage starts to accumulate in the form of transverse cracking, and at the tip of the crack you develop a delamination that separates the neighboring plies. And if we apply tensile loading in the transverse direction, then splits, axial resin cracking will appear in the zero lamina. These damage mechanisms, like matrix cracking, cause degradation of the overall stiffness properties of the laminate, and as we've seen, they can trigger delamination and eventually fiber breakage. The effort then is to develop mathematical models that will enable us to calculate the stresses in the cracked configuration and the damaged configuration in order to enable us to estimate what is the effect of matrix cracking on stiffness and strength, what kind of additional energy we require to develop delaminations from those matrix cracks, and ultimately perform calculations to estimate the long-term performance of the composite. And all this information will enable us to optimize the constituent properties, like the properties of the fiber, the properties of the resin, and design the interface that plays such an important role when load is transferred from the soft matrix to the hard and stiff carbon fiber. Those delaminations that they are triggered from those matrix cracks, they become more critical at the compressive loading. And here we can see a multi-directional composite laminate with an open hole loaded up to 90% of its ultimate compressive strength. There is no visible damage, but is there any damage? Of course there is. And we can see that in this slide where extensive local delamination accompanied by matrix cracks in the 0 plies and the plus minus 45 layers. And if you have a well-trained eye, then on the left-hand side at the edge of the hole, between those delaminations, you will be able to see fiber breakage in the form of fiber microbuckling, which is an instability damage mode at the fiber level. Here is this crack that resembles a fatigue crack in metals under tension, but here it is static uniaxial compression, and that crack at the higher magnification in the scanning electron microscope, we can see the backward fibers, and this is a critical damage mode, very brittle in nature. When it reaches a critical length of 2 to 3 millimeters, it depends very much on your material properties and the laminate stacking sequence, it becomes unstable, leading to catastrophic fracture. And then the challenge here we have is how to identify non-destructively those cracks before they become unstable. And the other challenge, of course, is how to develop better material properties to provide bigger resistance to the initiation and the propagation of that fiber microbuckling. Mathematics, again, will give us that solution, the solution of what is the critical stress at which fiber microbuckling will be triggered. And if we solve this fourth order differential equation, we can determine the critical stress in the 0 plies at which fiber microbuckling will initiate. And this is a function of the fiber properties, the modulus, the radius, the initial waviness, the fiber volume fraction, taking into account the interlaminar shear stresses, especially the tau zy, which can increase the fiber waviness and as a result reduce the stress at which fiber microbuckling will initiate. And the equation also takes into account the entire non-linear shear response of the matrix, which again has a huge impact on the fiber stability, especially when the matrix provides the lateral support to our fibers. We have spoken about that invisible damage and the mathematical equations that will enable us to optimize the properties of the constituents, to optimize the laminate sticking sequence, and derive expressions that will enable the designer to estimate the critical stresses at which matrix cracking or delamination or fiber microbuckling will be triggered, how much energy is required to initiate those damage mechanisms in order to develop systems that they are damage resistant. And then when damage does happen and that damage is extensive and visible, we need again those analytical or numerical models that will enable us to design structures that they can still perform in the presence of that damage, to develop structures that not only they are damage resistant, but also they are damage tolerant. Blast is a dynamic event, and here the aim is how to develop structures that they can accommodate that energy without getting perforation. And the energy will be absorbed in the form of extensive damage, but always trying to avoid perforation. Because in a pressurized cabin at 40,000 feet, it will be very difficult for the pilot to save the aeroplane and the passengers. So type of toughening needs to be determined by a suitable design scheme for any given structure and loading. Here is a metallic airframe, and you can see that it cannot prevent perforation. Even a carbon fiber cabin is not going to be able to prevent that perforation to take place. So we need a different solution. Since the monolithic metallic or monolithic carbon fiber, both systems are unable to contain that blast energy. However, the combination of metal and composite might be able to contain that blast energy. And then we talk about hybrid layered structures that enable us to optimize the strength, stiffness, and toughness properties. And here we see an example that goes back more than 2,000 years ago for the Achilles shield, where the designer introduces a layered construction which is very similar in design to those applied in modern aircraft fabrication. And the shield consists of two outer layers of bronze, two inner plies of tin, and one central lamina of pure gold. And the combination of these three different materials, they enable to build a structure that is strong, it is stiff, and under an impact event, it doesn't shatter. It provides toughness. It demonstrates damage tolerance. The Airbus A380, of course, the upper fuselage panels are made from glare, which is a multi-layered construction of aluminium plies and glass fiber reinforced composite. Here we can see a micro CT image of an impacted fiber metal laminate where the blast energy is absorbed by plastic deformation of the metal, extensive splitting and resin cracking of the fiber reinforced plies, and many delaminations between the neighboring plies. But you don't get perforation. And here we have a construction that is tough and accommodates the energy created during the dynamic event. We can make it even harder for the laminations to initiate by introducing thermoplastic veils at predetermined interfaces. So in this instance, the strain energy release rate associated with the lamination can be increased by 60%. And then the propagation of the delamination finds additional resistance because of the thermoplastic veils. Hybridization at the fiber level can also improve the damage resistance and also damage tolerance of the laminate. Glass fibers can be protected with polypropylene fibers and prevent early fiber breakage. So in this case, the glass fibers provide the stiffness and strength in our laminate, while the polypropylene fiber provides resistance to an impact event. And when eventually damage does occur upon heating the laminate, all the matrix cracking and delamination introduced during the impact can be filled up because the polypropylene fibers melt and fill those gaps. By repairing or self-healing those cracks, the laminate has recovered much of its original strength and stiffness. 3D weaving, introducing fibers in the through thickness direction, in the Z direction, it enables us to prevent those delaminations. And here again, you need those mathematical models to optimize the fiber architecture, which still is going to produce a light, stiff, strong, and at the same time damage-tolerant construction where delaminations are harder to happen, and when do happen, they do not propagate. This is a comparison between the two-dimensional fabric and the three-dimensional construction, where we can see on the left-hand side extensive delamination is taking place, but on the right-hand side, the 3D fabric, you have no delamination. You do get fiber breaks in both of them, but no delamination. And then the challenge is when you have these broken fibers, you have this open hole. Can your laminate accommodate the hole without actually suffering in terms of losing strength and stiffness? And here we compare the stress-strain response of the undamaged laminate and the damaged one with an equivalent open hole. And we can see that the 3D woven construction can function in the presence of the damage, in the presence of the hole. It does not really fill the hole. So we spoke about hybridization, where we mix layers of metal and layers of composite. We spoke about hybridization at the fiber level, where we protect the stiff and strong glass fibers with softer polypropylene fibers that also enable us to have some kind of self-healing process upon heating the laminate. We spoke about interleaf toughening, where we introduce thermoplastic veils at critical interfaces where delamination is expected. And there is another way of introducing toughness or making it harder for those cracks to be triggered. And this time we bring in graphene into play, where the more brittle epoxy resin is nano-modified with graphene platelets. Graphene is defined as a two-dimensional material, an allotrope of carbon, that can be used as additive for polymers and composites. And it is accepted as graphene provided that the platelet is less than 10 layers thick and less than 30 nanometers in thickness. We can produce graphene by removing elements from a large starting material like graphite, or we can assemble from a nanostructure from smaller elements, so we can build the material atom by atom. Electrical exfoliation is a top-down method, at present gram scale production of graphene, where the thickness of those platelets is between 2 and 4 nanometers, and the size varies between 140 to 200 nanometers. The chemical fiber deposition is considered as a bottom-up approach. We go graphene layer at 1000 degrees on a copper plate. Graphene material made by the two methods should be the same. In practice, though, no production method is perfect, and each has its difficulties, which lead to characteristic defects in the final material, and that can have an impact on mechanical performance. The mechanical properties of graphene, the Young's modulus is over 1 terapascal with a strength of 130 gigapascals, and a surface area, 1 gram, covers 2,630 square meters. Graphene in its pure form is transparent to light and electrons. The electrical conductivity increases by 12 orders of magnitude for a polycarbonate nanocomposite with 1% by volume of graphene platelets. The thermal conductivity also improves, in addition, of course, to mechanical properties like stiffness and strength. So graphene can improve composite performance, can provide better impact resistance, improve the fatigue life of the composite, and can be used as a strain sensor. Electrical conductivity increases, and that can provide lightning strike protection in our structure. And the presence of graphene in the resin can reduce water uptake. Also, a small amount of graphene in the polymer composite can provide resistance to fire. The unique combination of these properties ensures that graphene can be used for applications in a variety of fields like energy, bioapplications, optoelectronics, flexible electronics, and of course composites and membranes, since it enables us to build lightweight structures, strong composites with many functionalities. We spoke of the healing potential of hybrid composites, where the polypropylene fibers upon heating melt, filling up the gaps and the delaminations and recovering compression after impact strength of the laminate. Graphene now increases the thermoconductivity of the epoxy resin, and this has the potential of speeding up that heating process. Other incredible uses of graphene is the graphene filter, covered in tiny holes just big enough to let water through and small enough to keep salt out, making salt water safe for consumption. Another incredible use is a graphene antenna that could give us wireless terabit uploads in 1 second. This is the Magma UAV developed at the University of Manchester, which is used as a flying platform to demonstrate technologies developed in our research labs. The first wave of conductive fabrics that will carry heat or electricity around our body, but without any power source, have already appeared in the market. Carbon fiber composite aircraft are currently covered with a copper mesh for protection against lightning strike, and that adds additional weight to our composite structure. And the question here is, can we develop a conductive graphene modified epoxy matrix that could provide that protection? Today's composite challenges: increased supply of raw materials, always the need to reduce materials cost, reduce finished part cost, and reduce processing cost. We have to increase the speed and volume of manufacture, and machining, drilling, assembly, joining, and repair of these polymer composites, they provide additional challenges. And of course, they need to develop non-destructive evaluation techniques and real-time structural health monitoring methods that will enable us to monitor those cracks in the early stages in order to avoid sudden catastrophic failures. So we can see here the processing cost is between 60 and 75% of the total part cost. Automation and multi-head robots will reduce that production cost by speeding up the process. Already, robots have been introduced in the aircraft construction, and here we can see highly automated and digitally connected Airbus A320 fuselage assembly line in Hamburg. The other big challenge is the development of reliable models, analytical or numerical models, that will reduce the need of extensive experimental work at the ply level, at the component level, at the structural element, at the component level, and complete structure in order to evaluate the structural integrity, making the whole process very expensive. And those models, they need to take into account the original state of the component, accounting for the manufacturing method used to fabricate the part. Because the autoclave molding or filament winding or compression molding, they introduce different type of defects that we need to take into account in our damage mechanics analysis in the effort to estimate the strength, stiffness, long-term performance of the composite. A length scale arises because of the complexity of the nature of cracks for specific damaging mechanisms. And there is need to develop those quantitative relationships between nano, micro, meso, and macroscopic parameters in order to have confidence in our predictions. I would like to stop there and thank you all for your attention, and thank again the organizers for their kind invitation. Thank you and enjoy the event.